Welcome back to Algorithmic Game Theory. Over the last weeks, we've learned a lot about mechanism design with money. But what if you don't want to use money to push people into the right direction so that you actually get the desired outcome? Why wouldn't you want to use money? Maybe it's because it's infeasible to collect the money, or maybe because it's unethical for certain reasons. What can you do then? In the next following lectures, we'll get to know something about mechanism design without money. Unfortunately, things are much less clear then. The settings are usually more complicated for a very good reason, because so far everything that we were doing was in units of money. And by that I don't just mean the payments. I also mean how much do you value this item. Also this we expressed in terms of monetary units. We said, okay, I now value this item 5 and this item 3. And if you now have a higher value, then you should get the item because this is what maximizes social welfare. Now, if we don't have money, how should we compare what is more valuable? For whom? And as you see, we'll have to think about this more carefully, what we actually mean by getting a desirable outcome. The first problem I'd like to consider now is a very simple problem in which every of our agents brings one item to the market, which we call a house. And what they want to do is they want to exchange these houses so that everybody is as happy as possible after the exchange. You could, of course, also do this with money. So everybody just sells their house and then you buy again the houses. And this is maybe even a possible mechanism for such a setting. But here now we want to do this entirely without money. So what will this look like? As usual, we have n agents, I now call them for no really good reason, and those we could still call players. The set is called capital N, and each of them initially has one item, which we call house, just to say, okay, you actually only need one house to live in. You don't need two houses, but you definitely should have one house to live in. And what is now our goal? Our goal is to reassign these houses to make agents happier. Which means we want to find a one-to-one correspondence pi, which will just be a mapping from n to n, which means that after reassignment, agent I will have house pi I. Okay. So as I was saying, we are not doing this with money, so all this making agents happier, we won't be expressing in terms of monetary units. So of course you could say now, okay, I value this mansion by 2 million and this mansion by 3 million, and so I prefer a 3 million mansion to the 2 million mansion. But why does this make you, or why is it more important that you now gain 1 million compared to somebody else, so in perceived valuation than somebody else who maybe just is getting 1,000 more? And therefore, we are not expressing actually all these preferences in terms of monetary units. We don't say I value this house by this much, but we rather say, okay, this is my preference list of houses. I prefer this house over that other house. So each agent has a full preference list over all houses with no ties. Let's see what this may look like. We have agents A, B, and C, and they also bring a house, A, B, and C. And for example, the first agent might prefer house B over house C over house A. The second agent might prefer house C over house A over house B. And the third agent might prefer house A over house C over house B. Okay, in this case, things are really easy because the most preferred house, this is a different one for each of the agents. So we could just give agent A house B, agent B we could give house C, agent C we could give house A. And all of them would be happy. All of them would be the happiest people in the world because they got their favorite house. So our mapping pi would then be this perfect matching in this bipartite graph. But usually things won't be this smooth. Of course, there might be this one mansion that everybody wants to have, and then we can give everybody what they prefer most. For example, this might look as follows. So again, we have agents A, B, and C. Each of them brings a house, A, B, and C. And agent A now prefers house B over house C over house A, as before. But agent B now prefers house A over house C over house B. And the preferences of agent B we don't modify either. What would happen if we now did the same exchange? So, how happy are people now? Agent A still gets the preferred house. Agent B does not get the preferred house. Agent B gets only the second preference, and agent C gets again the most preferred house. But what could agent B now do? Agent B could just talk to agent A and say, well, you're getting my house. Agent B brought house B. What if just the two of us swapped houses? You would still get my house, and this wouldn't change anything, but I would then get your house, so I would be happier than what I'm getting here. And this is why we call this allocation unstable. Agent A would be willing to join this deal. Agent B would be happier with just this pairwise exchange of only agents A and B. Let's formalize this property of an allocation being stable or unstable. First, we say that a subset A of the agents is a blocking coalition of an allocation pi if there is an allocation sigma which only involves the agents from A such that no agent in A prefers pi of I over sigma of I, and at least one agent I in I prefers sigma of I over pi of I. And in this allocation here, we found a blocking coalition of namely agents A and B because there is this blue allocation. So this would be allocation sigma. The green one, this would be allocation pi. And so here we would have that A would be consisting of small a and small b. So in other words, a blocking coalition would rather trade the houses among themselves than using this allocation pi. And what we will be looking for is the following. Namely, we call an allocation stable if there is no blocking coalition. And our goal will be to find such stable allocations. Why that? Because this ensures, in an allocation being stable, if we find a stable allocation, this ensures that our agents are actually willing to take part in our exchange and they're not deciding to just drop out and do their own thing. But of course, the big question is there always such a stable allocation? And if so, is it difficult to find or not? Well, as we'll show, not only is there always a stable allocation, but it is also pretty easy to find with a somewhat simple algorithm. We'll now show that there is always a stable allocation, meaning that there is always an allocation such that no subset of the agents would want to do their own thing, and they would just rather want to trade houses among each other than taking part in our big exchange. How do we do that? We will devise an algorithm, namely the so-called top trading cycle algorithm. And this is actually a pretty straightforward algorithm. Namely, what we'll do is we'll first give each agent their most preferred house if we find a cyclic exchange this way. If we find an allocation that, okay, your preferred house is now my house and my preferred house is your house. For example, this would be cycle of length 2. This is something that we might start from. And we'll then successively eliminate these trading cycles. Let's formally write this down. We'll initialize n prime as the set of all agents, and while there are still agents left, we do the following. We construct a directed graph on n prime. Each vertex has one outgoing edge to the owner of his or her most preferred house among all houses owned by n prime. Importantly, it is also possible to keep your own house. And in this case, where does your edge go? Your edge will go to yourself. If your most preferred house of the remaining houses is your own house, then we will have a self loop just going back to you, and this then also counts as a cycle for what we're doing now. Because our next step is find an arbitrary directed cycle in this graph and to each I in the cycle assign the house owned by the successor in the cycle. And then we'll remove all agents on the cycle from n prime. Is this a well-defined algorithm? Well, to make this a well-defined algorithm, it will have to terminate, and it will actually terminate, and this was incorrect, while n prime is not the empty set, of course. So why does this work? This will work if we can always find a directed cycle in this graph. If there is always a directed cycle in this graph, then we'll always be removing some agents, and then over time, because we have only finitely many agents, over time we'll end up with the empty set, and this way will terminate. Why is there always a cycle? Well, that's the really easy following observation. Every directed graph without sinks has a cycle. What's a sink? A sink is a vertex without outgoing edges. But did our graph have such sinks? No, because every vertex has an outgoing edge, namely exactly one outgoing edge, to the owner of the most preferred house among the remaining houses. Why is this true? Well, this is just a standard observation as you usually do these in graph theory, namely start from any vertex, follow an arbitrary outgoing edge. Because there is always such an outgoing edge. And now keep following outgoing edges until coming back to a vertex that we've seen before. And then we have our cycle. And why does this always happen, that we come back to a vertex that has been visited before? This always happens because the graph is finite. Cool. So, this is a well-defined algorithm. Let's see what it does before we then analyze its properties. Namely, let's come maybe back to our earlier example. We had these agents' preferences. Agent A preferred house B over house C over house A. Agent B preferred house A over house C over house B. And Agent C preferred house A over house C over house B. So what's now the graph in the first iteration? We'll have 3 vertices and we'll add outgoing edges. What's the most preferred house of agent A among all these? This is house B. What's agent B's most preferred house? It's house A. And what's agent C's most preferred house? It is house A. So where's our cycle? Our cycle is here, or there could of course be multiple cycles, but this is one cycle that we see. So this means that we'll set that agent A will get house B, agent B will get house A, and then we'll construct the remaining graph, which only has vertex C. Among all remaining houses, which one does agent C prefer most? Well, they have to prefer their own house, and so we'll also find again a cycle, and then we'll have that agent C will keep their house. And I now claim that not only here we're getting a stable allocation, but always, which means that there is no blocking coalition. Why that? How do we prove this stability? Well, we have to show that there is no blocking coalition. How do we show that there is no blocking coalition? We assume that there is a blocking coalition, and then we'll lead this to a contradiction. Because then at some point, if there was a blocking coalition, then the algorithm would do something incorrect, namely not give one of the agents their most preferred house out of all remaining houses. So suppose pi is not stable. Then there is this a subset of the agents, and this allocation sigma, such that the following holds. Let A unequal be the set of all agents which are getting something different in the allocation pi than they're getting in the allocation sigma. Now what has to hold? It has to hold that this set won't be empty, and all I in that set prefer sigma I over pi I. Now this might be a little confusing, why this is a way to state that there is a blocking coalition. Didn't we say a blocking coalition, that's a group of agents such that some of them get happier and some of them don't care? And is this really equivalent? Yes, it is. But why? If you don't care, then because you have strict preferences, you are getting the same. So if you don't care whether you're getting what you're getting in pi or in sigma, then you have to get the same because you have strict preferences among all houses. And for everybody who's not getting the same, they have to prefer what they're getting in sigma over what they're getting in pi. This is what would make the allocation unstable. Now let's see what's happening. There is now this set of agents which are unhappy with our allocation pi that we are computing, which we will show that this cannot exist. Let's consider the iteration of the algorithm when for the first time an agent from this A unequal is removed from n prime. Because eventually all of them will be removed. Everybody gets something eventually. So let's consider the first time that this is happening. And we now let n star be the state of n prime before this allocation, before this iteration. Now what do we have? Well, this set A unequal, eventually they all have to get something, but first there's something happening and which doesn't involve all of them. Let's assume there's something happening which none of them is involved in. But then at some point they are getting something. The first one of them is getting something. So in n star they are still all contained. All of A unequal is still contained in the set n star, and then one of them gets removed from the set n prime because they're getting their most preferred house among all houses in n star, because this was how the algorithm is defined. We always, in each iteration, we always give an agent their most preferred house among all remaining houses. But the point will now be, why should the agent be happier with what they're getting in sigma? Where should that even be coming from, if we're now giving them what they prefer most? Because so far all that was happening in pi was anyway equal to sigma. Now something different is happening. But now if you're the one of them being removed, you cannot be made happier than what we are giving you right now. So more formally, we observe that sigma of I is also in n star, because otherwise we would have that sigma of I would be in a takeaway, a unequal. Why that? Because sigma of I is in the set A. All of A unequal is still contained in n star, so this would have to be outside A unequal. And what would that mean then? This would also mean that sigma of I got removed before because it was on a cycle. And on this cycle, sigma of I will have a predecessor. Which means that sigma of I will be equal to pi of I prime, which will be equal to sigma of I prime for some I prime, which is in A takeaway A unequal. And this would be a contradiction because I prime could not be equal to I. And now we've seen that sigma of I is an n star, and by definition pi of I is I's preferred house in n star. Why was that? We were saying that we are now removing agent I. Agent I would get sigma I, but sigma I, this would actually be an option now. And we're giving agent I now the preferred house of all this. And so as pi of I is n star, sigma of I is n star, this is now a contradiction that I prefers pi of I over sigma of I. And this proves our claim. So as we see, we are not only is there always a stable allocation, we are also able to find this via this very simple top trading cycles algorithm. Namely, we suppose that if the allocation was not unstable, that then at some point we didn't give the agent, one of the agents, their most preferred house among all remaining houses, which would be a contradiction. What we'll be doing next is derive some further properties of the stable allocation. Namely, what we'll show is that this is actually the unique stable allocation. And we'll also come back to our standard question: what if you misreport your preferences? Can you benefit from misreporting your preferences here, or can't you? We'll now be showing two further properties of the stable allocations in our house allocation problem. The first one being that the stable allocation is actually always unique. So while we already know that there is a stable allocation because the top trading cycles algorithm computes it, there could be multiple so far, but this is actually not true. Namely, the allocation pi computed by the top trading cycles algorithm is the unique stable allocation. How do you prove such a theorem? If you want to show uniqueness, what you usually do is you now have already this one allocation that you now want to see and that you want to show is unique. So take any other stable allocation and show that eventually this other stable allocation has to be equal to pi. So let pi prime be any stable allocation. Furthermore, we let nt be the set of agents allocated in the tth iteration. Now what we'll do is we will show that pi of I is equal to pi prime of I for all I in nt and this holds for all t via induction on t. Now the base case of this induction is that t is equal to 1. By definition, all I in N1 get their favorite houses. And furthermore, setting A to N1 sigma as mapping from N1 to N1, which gives each agent what they're getting in pi, is not a blocking coalition for our pi prime, which is our stable allocation that we're comparing ourselves to. Now, if pi prime of I is not equal to pi of I, it would be a blocking coalition. And by that I mean for any I in N1. Why that? Because everybody's getting their favorite houses. So what they'll definitely have to get is what they're getting in pi of I. Good. So this means that pi prime of I is equal to pi of I for all I in N1. And let's now consider the induction step. So t will now be greater than 1. And we know by induction hypothesis that pi prime of I is equal to pi of I for all I in the union of all these nt prime. What does this mean? This means that both pi prime and pi reallocate houses inside the current set n prime, which is exactly the remaining agents. But this looks exactly like the case when we started the algorithm with just the set of n, just the set n prime of agents existing and no other agents existing at all. So what we can say is that This is the exact argument as in the base case. If n take away n prime never existed. So as we see, the stable allocation is even unique, and it's a little hard to write this down, but I think eventually it's not that surprising if you think about this carefully. Because what you're doing in the first iteration, there's no way around what you're doing there, because otherwise you would already have a blocking coalition. But if you think on from that point, then you see, okay, now what I'm doing in the first iteration, that's set in stone. So it doesn't actually matter whether or not these agents exist, because they have to be trading among each other anyway. So I can just remove them from my consideration, and then I'm getting a new first step. And also in this new first step, okay, I'll have to do it just the way I'm doing it for the exact same reason. Cool. Now the next property I'd like to discuss is, do you actually want to lie about your preferences? Could you be better off here? And the interesting result is no. Lying about your preferences would not make you better off. Why that? So no agent can improve his allocation by misreporting the preference list. To see this, fix agent I and other agents' preferences. Like we've already always done this when we were talking about misreporting the preferences, we now fix everybody but player I, and we see what can player I now do. And as before, we again use the notation that NT we call the set of agents who are allocated in the tth iteration and we let T star be the allocation, be the iteration in which agent I is allocated a house when reporting true preferences. Now, what might be beneficial for Agent I? Agent I sees actually in these earlier steps, in N1 through NT star minus 1, there the better houses are allocated. Those are the houses that I prefer most, because in round T star, I'm getting my most preferred of all remaining houses. By now misreporting my preferences, I could move myself further to the front. I could probably get an earlier house. But what I won't be getting is one of these houses that were actually allocated earlier. And why that? Because there was no incoming edge. And I don't have any influence on incoming edges. What I'm relying on to be allocated is that somebody else likes my house. And this is not what Agent I can influence. Agent I can only misreport his or her own preferences, but not make sure that somebody else now suddenly likes her house. So, by misreporting, Agent I could be served in an iteration before T star, but will not receive a house from this union of all houses that were allocated before T star. No matter what Agent I reports, he or she will always get a house from that other half. So from T star onwards, and the allocation by the algorithm when reporting true preferences is the most preferred of these houses. And this proves our claim. So as we see, there's also something like truthfulness in mechanism design without money. For some reason, it is often then called strategy proofness, but it is really the same thing. You want to report your true preferences because otherwise you will be worse off, or at least you won't be better off when misreporting your preferences. And the arguments, they look very similar to what we are seeing in the context of mechanism design with money. Namely, we see, okay, I actually cannot influence what the other agents are reporting. So given what they are reporting, I'm actually best off by also reporting the truth. And this is exactly also coming across in this argument. Maybe it's a little more wordy than these nice inequalities that you would see in the context of, for example, a second price auction. And this is maybe because we didn't introduce so much notation here, but also because we are just not comparing this, these utilities in a way that we just say, okay, this is the larger number than that one, but we rather just do this comparison by these ordinal preferences that you say, okay, I prefer this one over that one. Next, we'll see another setting, which we can also, in which we'll also want to do mechanism design, but certainly without money for ethical reasons. Now let's talk about a different setting in which you want to use mechanism design, but for ethical reasons you actually don't want to have money involved in this, and this is kidney exchange. What is this all about? I think you've heard of cases where people donate kidneys, for example, to their relatives. One prominent example would be Germany's now President Frank-Walter Steinmeier, who donated one of his kidneys to his wife about 10 years ago, and then both can live with just one kidney instead of two. And in this case, this just worked out fine because he and his wife, they had compatible tissue, so his wife could actually receive a kidney from him. But what if you don't have relatives whose tissue is compatible with yours, but you have relatives who actually are willing to donate a kidney? Then maybe somebody else, somewhere else, has the same problem. They also have relatives who are willing to donate their kidneys, but again, they are not compatible in terms of the tissue. What is very plausible then, what you can do is you can swap the kidneys. So your relative is then donating their kidney to this other patient, and you, as the patient, are receiving a kidney from somebody else. And the idea is now to make just these matches. That, well, what you could, for example, do is do exactly what we were doing in the case of the top trading cycles algorithm and with these stable allocations. You could now try to find a reallocation of the kidneys such that everybody gets their preferred kidney among all kidneys that are available for exchange. And this is indeed something that was proposed. So very explicitly now, each patient-donor pair then becomes an agent in this stable allocation problem. Agent's preferences express how likely it is that the other agent's kidney is compatible. And then we hopefully get a cycle of kidneys to be transplanted. Then there is the patient-donor pair A, the patient-donor pair B, the patient-donor pair C, and maybe then A gets the kidney from B, B gets the kidney from C, C gets the kidney from A, and so on. I think you're convinced that this is certainly a setting, at least for me personally, where I don't want to see money involved, and indeed, at least in Germany, it is forbidden to sell organs for money. And at least also for me, ethically, this feels like the right thing. So would you maybe want to apply this this top trading cycles algorithm in a kidney exchange? Feels like a good idea, but unfortunately there is one flaw, namely we now have, for example, a cycle of length 10 or so, meaning 10 kidneys being transplanted, just to come up with one number here. But this means that because every transplant corresponds to actually 2 surgeries, we'll have 20 surgeries, and the point is that all of these surgeries should actually happen at the same time. Because otherwise you'll have the situation that somebody has already received their kidney but not yet donated. And the way you should think about this, there's a patient and a donor. Those are 2 different people. The patient has already received the kidney, but the donor has not yet donated it. And then there is actually no law that requires you to now donate the kidney. And this is why all these surgeries will have to take place simultaneously. And this is just infeasible. And therefore, there is also a different algorithm which has been proposed, a different approach to this entire problem, namely to only consider pairwise exchanges. And what can these pairwise exchanges look like, and how could we model that? We are now also using a simpler model to express tissue compatibility, namely we just say, okay, this is compatible or this is not compatible. So what can this now look like? We have a patient-donor pairs. Those will be vertices V in a graph. And we'll have tissue compatibility This is expressed by simply edges between vertices. Our goal is to find a maximum cardinality matching. So we want to make people as happy as possible. And because agents can actually deny any surgeries without stating any reason, the situation that we are facing is that actually these edges, those are private information. And what we will see is that they just report some edges, and the question for us is, do they report all their edges? So the edges E are private information, and each I in V reports set Fi, which is a subset of Ei, where Ei is the set of I's neighbors. What is now our goal? Our goal is to design a way to find a maximum cardinality matching such that also agents report their true neighbor set and not just only a subset of this. Why should they maybe only report a subset? Because maybe if they only report a subset, it makes it more likely for them to be given something, or it makes it more likely that they get a very good match or something like this. Because this is something that people have also thought about. Why don't we first give kidneys to the ones who are really difficult to match? And then what will happen is that eventually, because this is somehow private information, this is somehow the outcome of what the respective doctors find out, eventually everybody will say, okay, I'm really hard to match. I have a very complicated tissue, I have only few relatives, or I have only one relative with a very special tissue type who can donate, and I don't have multiple relatives who will have many different ways of being matched with different tissues. So this is why you want to design a mechanism such that every agent wants to actually report all of their compatibilities. They don't want to just report a subset. And indeed, there is a mechanism, or in other words, a matching algorithm, which allows this. Namely, what we do is we collect a report Fi from each agent I. Then we let F be the set of reported edges. So we'll have this pairs I, j, where I is in Fj and j is in Fi. Now we let M0 be the set of maximum matchings on V, F. And now we consider the agents in any order that is independent of the reports we now let Zi denote the matchings in Mi-1 that match vertex I, and if there are such matchings, we let Mi be equal to Zi, otherwise Mi will be equal to Mi-1. And then the last thing that we do is we will return an arbitrary matching in Mn. This algorithm feels a little exponential time because it states, okay, now compute all possible matchings, and this might be super many, but there are also much more efficient implementations of the exact same idea, but this is the easiest way to analyze what's happening here. So what is it that we're doing? We have our reported graph. Each agent is claiming some preferences, some compatibilities. We now let M0 be the set of all maximum matchings in this graph. And now let's consider the first agent in any order. The first agent, we now see, is it possible that this agent gets matched somehow? Is there a maximum matching which involves this agent? If so, we will only, from this point onward, only consider matchings in which this agent gets matched. Otherwise, okay, this agent cannot get matched, so let's not care about him or her any further. Then we get to the second agent. And now we ask the same question. Among all remaining matchings that we are still thinking about, is there one that also matches agent 2? If so, then again restrict your attention to only matchings that involve this agent. Otherwise, okay, just move on, because this agent will never get matched. And eventually, when we reach the set Mn, then we're in the situation that the set of agents who are matched is the same in every matching. Only how they are matched, this might differ. And what we can now show is that you actually don't want to misreport your edges. So our theorem will be given any reports of the other agents, if agent I gets matched when reporting any Fi, which is a subset of Ei, he or she also gets matched when reporting Ei. Now, how do we prove this? We'll have to have a closer look again at the algorithm. What happens now if you change your report? The first thing that can happen is that these maximum matchings actually become different. So these are the matchings of maximum cardinality. And one thing that might happen is that suddenly more matches can be made if you're reporting more edges. But this is great, because then you are involved in every maximum matching. Why that? Because if you weren't involved in such a maximum matching, then this matching could have been made before. Good, so it might happen that actually we'll get not only more maximum matchings, but also the cardinality of these matchings will increase, but this is only possible if we are always matched, we as the agent are always matched in any of these maximum matchings. Or the alternative is that the number of matches in such a matching does not change, and in this case we'll have to have a closer look at what's happening down here. And then what we'll have to see is that actually we'll leave the algorithm just more options, which means that when it's our turn, then we are not eliminated down here, or maybe not eliminated down here. We are certainly not eliminated down here when we weren't eliminated before. So what is happening here? Maybe I wasn't precise enough earlier. If there's no maximum matching involving you, then you won't be matched. Otherwise, you'll be matched for sure when it's your turn. So let's write this down more formally. So if under report EI the maximum matchings have higher cardinality, then under Fi, then I will be included in every maximum matching. And so, because we are computing a maximum matching, I will always be matched. Or, otherwise, the cardinality of the max weight matching does not change. In this case, now let Z0 to Zn be the sets generated under report Fi, and Z0 prime to Zn prime be the sets generated under report Ei. What can happen further? If Zt prime is a subset of Zt prime prime for all t prime which are at most I, then we in particular get that Zi prime is a superset of Zi, and this means so I will get matched under Ei when he or she gets matched under Ei. Now the only way this cannot happen is that one of these sets will be empty if reporting fi but will not be empty when reporting ei. But then I is matched in every matching in z prime subscript ti, and so I will always be matched. Okay. So this is again a little complicated as to write down as the argument, although actually the insights I hope are not very complicated to see. The point is, when you are now reporting your edges, you are only offering the algorithm more options. And because you're only offering more options, it might be that you change the course of the algorithm. Maybe you're not changing the course of the algorithm. Then you're matched if and only if you were matched before. Or something changes now, but then things change into your advantage. Namely, then this is because of your additionally reported edges. Because if your additionally reported edges, you now are considered crucial for the maximum matchings, and this is why you will definitely get matched. What is maybe a little implicit in the way I wrote down this argument is that all of this relies on the fact that we are not making this order depending on the reports. And as it turns out, this proof will break down if, for example, you go through the agents by decreasing or increasing degree in the graph. Because then suddenly you would have an incentive to misreport because you want to make your degree as small as possible. Things like these. I hope you see that generally mechanism design without money isn't a lot different from mechanism design with money, in the sense that you can still ask the exact same question. Do you want to misreport? And why don't you want to misreport? The thing is, expressing preferences is much more complicated because we don't have these monetary units which we were using before. But eventually, there are also some very nice arguments, some very nice mechanisms, one of which we will also see in the next lectures. And you will get to the point that so there's no such general theory as like Meyerson's lemma, as VCG, but for many specific settings, you will see there are very nice results. Although I can now already tell you, having this property that you don't want to misreport your preferences, this is something that we will often not be able to achieve, at least not for everybody. So that's it for today. Please let me know if you have any questions. See you next time. Stay safe. Bye.